Okay, we'll just for like wait for maybe one more minute and then we'll start. Okay, I'll I'll start by sharing my screen. Moment. Is my screen visible? Hello?
Yes, it is.
Okay, okay, cool. So today I'll cover some topics related to statistics. Most importantly, like normal distribution, because we have seen a lot of questions related to normal distribution. We have seen questions related to other distributions also, like maybe binomial, Poisson, etc. But a lot of questions are focused on normal. So we'll cover some topics related to normal distribution and some basics of hypothesis testing, like what is testing, how to formulate hypothesis test, and maybe a couple of examples if we get time. And then I will try to cover some confidence intervals also, how to calculate confidence intervals, and what is the difference between confidence intervals and what you do in hypothesis testing, things like that. If we after that maybe we can talk something about correlation, covariance, etc. But mostly those are like probability related topics, so I will focus mainly on stats. Okay, so normal distribution. So, see, basically, normal distribution is a continuous probability distribution. It is a continuous probability distribution. It actually tells us that a continuous distribution means it tells us the random variable under question. It can assume any particular value uh, in an interval. So by continuous, we mean that the number of values that the random variable can assume are uncountably infinite. If it is countably infinite, then we say it is, if it is countably infinite or finite, then we say it is discrete distribution. Okay. So since it is continuous probability distribution, by definition, the probability of the random variable assuming any particular discrete value, it is always zero. We are only focused on the values, the probability of the random variable assuming it in a particular interval. Okay, please understand this. So here probability is in continuous distributions. Probability is interpreted as the area under the curve over an interval, and this curve is called the probability density function. So, in continuous probability distributions, we have discussed that the random variable takes an infinite number of values. It should actually be uncountably infinite number of values. And this is another thing that you should be aware of. For any probability distribution, you take any of them, the total area under the curve is always 1. This one, right? Total area under the curve is always 1. And the probability that the random variable assumes any particular value is 0. So your normal distribution, it looks something like this. It is also called a bell curve because it looks like a bell, right? And the area under this entire curve stretching for negative infinity to positive infinity, that is 1, irrespective of the kind of distribution you are looking at. So some key characteristics of this distribution are that this distribution is symmetric about mean. This line that you see here, this is the mean, and you can see that this curve is symmetric about this mean. Not only mean, this curve, this line you see here, this is also the median, and this is also the mode for standard deviation, normal distribution or Gaussian distribution. So if somebody asks you about Gaussian distribution, you should know that it is normal distribution, right? So for a Gaussian distribution, it is a characteristic that the mean, median, and mode are equal, and the curve is symmetric. The probability density function, this curve is symmetric about the mean. Mean is mean equal to median equal to mode. This is a characteristic, and the tails approach the horizontal axis here. This is a tail, this is called left tail, and this is another tail, this is called the right tail. These two left and right tails, they approach the horizontal axis asymptotically. That means these do not touch in the real line, but they keep approaching the x-axis. By asymptote, I hope you understand what it means. And this particular probability density function for normal distribution, it is defined over the entire real line. There are no breaks in between. No, the probability density function for normal distribution or Gaussian distribution, it is defined by this f of x, where x is the random variable, that is 1 by sigma root 2 pi e power minus half x minus mu by sigma whole square, right? Where sigma is the population standard deviation and mu is the population mean. Now, what from this what we get is that f of x, this probability density function, it is the height of the curve at any point x. You take a point x here, so the probability density function is the height of the curve frequency at which the corresponding value occurs. Okay. Now, any probability density function of normal distribution is defined by two parameters only: mean and sigma, mean and standard deviation. If you know mu and sigma, you can construct the entire normal distribution. So you can draw normal distribution for any mu and sigma combination. So there are many different normal distributions, one for each mu and sigma pair. Okay. No. So, since there are many many normal distributions that occur, depending on mu and sigma, these are uncountably infinite number of normal distributions. We take one of these distributions, and call it the standard distribution. That is with mean 0 and standard deviation 1. So we call this as Z, and we name this as the standard normal distribution. So the Z distribution has mean 0 and sigma 1, And if you substitute mu equal to 0 and sigma equal to 1 in the original equation, the PDF of the standard normal distribution you obtain as this: 1 by root 2 pi e power minus x square by 2. Any normal distribution, any normal distribution that you can think of, it can be converted into a standard normal distribution by transforming the normal variable into the standard normal form. You do this by subtracting mean and dividing by sigma. This is called standardizing the variable. So you have x as a random variable. This is a constant. This is the mean of the distribution, but this is a constant. And sigma is the uh, standard deviation of the population, and this is also a constant. So your x minus mu divided by sigma is another random variable, with mean 0 and standard deviation 1. Since x is a normal distribution, any arithmetic modifications like x plus some constant or x divided by some constant, all of this will result in normal distributions only. You can mathematically prove that by maybe here you can take y is equal to x minus mu by sigma. So x will be what, y plus sigma y plus mu. You can substitute that here. You will get the standard normal form. Standard normal form. So this is called standardizing the variable. So z-scores. See, to calculate the probability of some interval, what you have to do is you have to find the area under the curve. This is what we have discussed. Just give me a moment. I'm facing some issue. Just give me one moment, please.
Yeah, just I want to ask a question like while calculating the G score in hypothesis testing, why are you dividing the Z score by like the same expression by root n?
Uh, where?
Like when we are calculating the like Z score, we like for hypothesis testing in Z test, it is the same formula x minus mu by sigma by root n. So why are you dividing the sigma by root n there? Here also we are calculating the same Z score, no?
Are you making use of sample mean there, x bar there, or x?
Yes.
So if you are making use of x bar, the standard deviation that will have to be divided by root n. We will discuss that. I have not
Okay.
included that, but I will explain that later.
Yeah, and like just while since you're explaining the same thing, like just also explain one thing, like that's the why the standard deviation of sample like for the sample and population is different. Like for population we are dividing by capital N, and for sample we are dividing by n minus one. Why is the same? Like why you do that? Like
Okay.
last year in one of the interview I have seen that they have asked the question, but I did not get
Okay.
the answer, like correct answer.
Okay.
Sir, I have another doubt also in the hypothesis testing. Actually, the we use the p-test, right? You know what?
Yeah, yeah. We'll discuss all these things. Don't worry. And if we don't discuss, then definitely ask me. In the end, I will explain.
Like Akash is just requesting you to like do a like this type of discussion for hypothesis testing also. Like then okay, 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 sure. Thank you.
Okay. Yeah, I actually have a pen tab, so I thought like I will write down and explain, but somehow it is malfunctioning. So just a moment. Okay, maybe I'll have to do it like this. Okay. Okay, I'm sharing my screen again. I found a workaround. I hope my screen is visible now.
Yes, yes.
Yeah, I'll keep it like this instead of making it full screen so that I can write down if something is needed. Okay, so yeah, okay, okay, we were here, right? Okay, so suppose you want to find the probability A comma B. So see, you should understand that whether this is an open interval or closed interval or one side open, one side closed, it does not matter. It is that is because this essentially means probability of A less than X less than B. Whether you have A less than or equal to X less than B, or A less than X less than or equal to B, or A less than or equal to X less than or equal to B, it does not matter. That is because we know that probability, this probability, this is a continuous probability, right? And continuous probability means at a discrete point like A or B, the value is probability would be zero, right? So whether you have open interval, closed interval, it does not matter. Now, so what we usually have is that you have the probability density function, and in order to calculate what is the probability between A less than X less than B, what you have to do is you have to integrate the density function from A to B dx. I hope everybody is aware of this, right? Now, what happens here is that this is difficult to integrate. So for this purpose, what we have is we have normal distribution, standard normal distribution tables. So what they give is the probability of calculating the value from 0 to that point z. So tables provide areas under the curve from 0 to z. So tails can be computed as 0.5 minus area under the curve from 0 to z. So if you think of this as your probability distribution, a PDF. So if you want to calculate from here to here, this is the, suppose this is z, then you have probability of x less than z. Okay, this you can do it as 0.5 minus probability of minus 0.5 less than sorry, not minus 0.5, probability of z less than x less than 0, and from your these tables you can find this value. So this is nothing but probability of 0 less than x less than minus z, right? This is because the normal distribution is symmetric. So this is why we only have from 0 to z in the uh, in your tables. Now, so for example, you want 0 less than x less than 1.28, then the area will be, this is from the table. You can look it up in any of the standard tables. It will be the same. And supposing this x follows a normal standard normal distribution. If it is x minus 1.28, sorry, x less than minus 1.28, then you will do 0.5 minus this. If it is 0 less than x less than 0.87, then you can just look it up. If it is minus 0.87 less than x less than 0, then then also it would be the same, because probability is symmetric. Now, this is here is one question. You can take this down. So, if the weight of males is normally distributed, that you know, with mean 150. Okay, 150 kgs is too much. Maybe for the purpose of theory, you can think of it. I just copied this example from some text. So 150 kgs and standard deviation is 10. So what is the probability that randomly selected male will weigh between 140 to 155 kgs? So we are given that this is normally distributed between with mu and sigma square. Sigma square is the variance. So whenever you say the parameters as mu and sigma square, you calculate the z scores. Z scores would be 140. This is for the lower bound and upper bound. I'll just do like this. 150. So what you want to do is you want to convert this into a standard distribution, so as to look it up from the table by 10, and 155 minus 150 by 10. So this would be -1 less than, suppose this is z, standard variable, then this is what you are looking for from the normal standard normal table. That comes out to be 0.5328. So this is how you will calculate a problem, solve a problem. Now, there are other types of normal distribution as well. You should understand that normal distribution comes in some varieties. The one that we study is the most general form, and then we studied the standard form. Um, so there are other types, such as beyond symmetric model, you have clamped normal distribution. So clamped normal distribution is when you want to clamp this normal distribution between 2 points A and B, right? You want to clamp this. So you want to remove these parts, and you want to say that only between A and B you want the distribution. Now remember that this may no longer be symmetric, may no longer be may no longer be bell curve. If you clamp this off, this is because you also need to normalize it. You also need to normalize your distribution, so that the area under curve comes out to be 1, right? You are removing this part and you are removing this part, but then what you are doing is you are taking this part, normalizing it, so it may no longer be a bell curve, but the area should be 1, because you are normalizing it. Okay. So this is useful when you feel like something should only be between A and B, and beyond B it is nonsensical. Something is normally distributed, you know that, but beyond these limits it is just nonsense. So you don't want to have it there. And you can also have what we call skewed distributions. So in skewed normal distributions, what we have is it is asymmetric. It is asymmetric about the mean, unlike the normal standard or general or standard normal distribution. So it will be looking something like this, or right. So at one end point, the tail will be longer. So whichever way the tail is longer, you will say the distribution is skewed towards that way. So this is a right skew. This is a left skew. Okay. So we use another parameter called alpha to define the shape of the distribution, and we have the probability density function as this. This defines the skewness of the distribution, where a positive alpha signifies a right skew and a negative alpha signifies a left skew. So for example, you are dealing with the salaries of maybe employees. In that situation, you will have a right skew, because a lot of people will be in this place, and but there will be outliers who are getting extremely well paid, right? But they will be very less in number, so they will be towards the right end of this. You will have a right skew distribution when you're dealing with maybe salaries, right? And also maybe dealing with marks in a very competitive exam. So a lot of people will be scoring at one level, but as you go higher, the values, the number of students or candidates having very high values will be very less, right? Those kind of things will follow this right skewed distribution. Okay. So skewed distributions are quite useful in various ways, and you can study them. But I don't think they would really expect you to know beyond these, and I mean, they would be insane to expect. But just for the purpose of completeness, I've put some more. No. So the heading should be changed, I think. Okay. Now, given any problem, so these are like some tips that you can think of. Always draw a picture of the distribution, whichever distribution you are dealing with, whether it is normal, binomial, Poisson, geometric, maybe chi-squared, T distribution. A picture really helps you understand what kind of a distribution you are dealing with. Okay. And then for normal distribution, just like for normal distribution, for chi-square, for T distribution, for F distribution, you have tables, because for them it is very difficult to find probability for other kinds of distributions, right? So use those tables very properly, correctly. Understand what area you are looking for in the table, and then practicing with real world examples really helps you. Okay. So before we go into hypothesis testing, so somebody asked me about X bar, right? So standardizing the X bar random variable. So let us take a moment to maybe discuss that. So when you are dealing with some experiments, what you do is you collect some samples, and to estimate the mean of the population, what you do is you take the mean of the sample, right? This is something you don't know, and you want to find this, right? What you usually do is you collect a sample and find the mean of that. That is your sample mean, right? So this sample mean, basically what you're doing is you're maybe collecting n data points from this distribution, and then aggregating them to find the average of those. But the n data points you are collecting, each one of them is a random variable in itself. Until you collect it, you do not know what it is, right? So suppose your data points are x1 to xn, right? Each one of them is a random variable. Since you are collecting all of this from the same distribution, all of them will have same mean and same variance. And we are again assuming that these are being collected from this distribution independently. Okay. So this is a very powerful assumption that you will come across if you are studying statistics, probability, etc. IID, which means independent and identically distributed. Since you are collecting from the same distribution, so all of these are identically distributed, and we are assuming that they are collected independently, right? Now, since the question we are discussing was about normal distribution, suppose the population is normal. Suppose the population is normal mu sigma square. Then we have one property of normal distribution, that if we add two normal distributions, we will get again a normal distribution. That is, suppose you have x1 as normal mu1 comma sigma 1 square, and x2 another random variable normal mu2 comma sigma 2 square, right? So when you do x1 plus x2, you again get another normal distribution mu1 plus mu2, and the variance would be x1 plus x2. Variance would be, suppose that variance is sigma square. We will discuss about this later. Okay. So, okay. Now here, this is because mean is also called expected value, and it is linear. So we can do like this. Okay. So to calculate variance, what we do is variance is calculated as expected value of x1 plus x2 uh, this square minus whole square. Here note that this is this. Okay. If you simplify this, what you will get is sigma 1 square as 2 times covariance of, right? So I hope all of you are acquainted with these kind of notations. What is variance, what is covariance, etc. So that's why I'm kind of directly jumping into this. Sorry, this is positive. Okay. So now since we are independently distributed samples, we are collecting that the covariance will be 0. So that would be sigma 1 square plus sigma 2 square, right? So this sigma square. Now, you are looking at, suppose you are first looking at sigma xi. What is the distribution for this? This is normal distribution with some mu comma sigma square. Sorry, maybe you can say mu prime. No, that would be confusing. Mu1 or mu1. Suppose this is your sigma xi. Then what will be your mu1? That would be expected value of summation xi, right? We know expected value is linear, so this would be summation expected value of xi. So this would be n times mu, right? Each of this, we know that it is coming from this distribution. Each xi is coming from this distribution, population. So your x bar would have mu as the mean, because sigma xi has n mu. X bar is what? Sigma xi divided by n, right? So the expected value of this is n mu divided by n. This is mu. Is it clear till now? Yeah. Whoever asked this question, is it clear till now?
Yes, yes,
Okay.
yes.
Now coming to the variance. Variance is, just a moment. If you take variance of x bar, what variance of summation xi divided by n, right? X bar is summation xi divided by n. Now, variance, what happens to variance when you multiply with a scalar? The scalar comes out as a square. Okay, that is because suppose you take expected value of some scalar alpha into some random variable y, this would be alpha times expected value of y. Now what would be expected value of some alpha y whole square? That would be alpha square expected value of y square. Just scroll. Alpha times expected value of y square. Your variance, it is calculated as minus, right? This alpha square will come outside, and the internally it would be variance of y. You can check that later, right? So using the same logic, what we will have here is 1 by n square. So what we have seen about summation of xi, if they are independent, their variance would add up, right? Here we have seen that variance of x1 plus x2, that would be sigma 1 square plus sigma 2 square if they are independent. Here we have assumed that in our sample all of those are independent. That means all of their variance will be added up. For sigma xi, that would be sigma square, n times sigma square. So this is sigma square by n. Okay. So variance of x bar is sigma square by n, and variance of x bar is mean, mu, population mean. So this is the reason. Uh, so if you take x bar, this would be normal distributed with mean mu and variance sigma square by n. So if you need to standardize this, a z value would be x bar minus mu divided by standard deviation would be what? Sigma by root n.
Okay, understood.
Understood? Yeah.
Yes.
So this is the reason why we actually put a square root n here.
Okay.
Okay.
just
Now,
just like for like if you are asked in the interview in a single line, we can say that like since here we are taking the mean of the whole sample, that's why we are dividing, like that's why it is coming to be
yes,
division by root n. And
you can.
otherwise if we are like for norm that like for, in
Yes,
normal case for a normal distribution, we are looking into a single one one set of
if you are
observations.
taking
That's why
one observation,
yeah.
yes, if you are taking just one observation, then it would follow mean mu and sigma square. But since you are taking sample mean in itself is a random variable, right? This random variable will have this distribution mean sigma mu and standard deviation sigma by root n. So that's why you divide by this. If they ask you to show why it is sigma by root n, then you can show all this. Okay,
Okay.
clear?
Yes, and just one more thing, like since it is to this concept of the like real life difference between variance and standard deviation. Like we know that one is the square root and one is the square, but if, like what is the
I
significance
didn't
if they
understand.
ask,
Could you
you
repeat
can
that?
like what is the difference between variance and standard deviation? Like
Difference between
significance wise,
variance and standard deviation.
yes, like significance say standard deviation is square root of variance, but like why we use both? Like what is the need if they ask like that? I mean, like
Okay,
analytically, how
see,
can you
the
need it? Like,
reason we go for variance is that if we don't go for variance, if we don't square the items, then the dispersion will be zero, right? If you just take x as random variable, mean mu, you want to find the dispersion of each value from mean. If you do like this, if you take summation of each xi minus mu divided by n, this will be zero, right? You know this, right?
yes,
This is always zero. The reason we go for variance is that this should not be zero. We don't want this to be zero, so we do this instead. Okay, this gives us variance. Now the problem here One problem here is that this the units of variance and the units of mean are not same. Okay, if you are dealing with something like just in the previous example, we were discussing about the weight of individuals, right? And we are saying average is 150 kg. Okay, and then we are talking about dispersion, and suppose it is coming out to be 100 kg square. What does this mean in real life? It is meaningless, right? It does not give us any idea of what kg square is. Instead, if we take a square root and then talk about 10 kgs is dispersion, it is like distributed around this like this. This is 10, this is 10. Maybe like this, there is some kind of dispersion. Then that makes sense. That is one reason.
Okay,
You get what I'm talking about?
okay. Like analytically, like definition wise, both are kind of same. But if they ask like analytical difference, these two are analytical difference. Like why we
Yeah,
need.
yeah. You can say about this. Apart from this, at the moment, I am also not able to think. Maybe I'll have to search why.
Sir, then directly we can calculate standard deviation itself. Then why variance is needed here?
You generally, for the purpose of maybe normalizing only, you use standard deviation. Um, Usually, we go for variance only. Variance is kind of a central moment, as in, if you know moment generating functions, there you will get this. You will get this idea called x minus mu whole power r, right? These are central moments about the mean, and you put r equal to 0, r equal to 1, r equal to 2, etc. So variance comes out of this when you have r equal to 2, right? So that is for the theoretical part. Uh, but standard deviation by itself does not come out of any of our equations. We use standard deviation for our maybe convenience. That is as much I know about it.
Like, will they go so much deep into the concept like studying about moments because
So have you done a probability statistics or maybe some masters in mathematics, something like that?
no.
In that case, you can safely assume they won't go too much in depth. If you have studied probability statistics previously, they may go into in depth. They can ask about there have been instances where they asked about moment generating functions, etc. But that is for people who have maths background,
Okay.
because they are expected to know all those things. And even if they ask you about these things, you can safely say that I only have certain amount of understanding of probability. I don't have that much knowledge in there. Because since you are going there to study all this, they cannot assume or say that they cannot assume that you know maths. Then there is no point in going there to study, no?
Okay.
Right?
Okay.
No. Yeah. No. Coming to the second question, somebody asked about sample variance being divided by n minus 1,
Yes,
whereas
yes, I only
population
have.
variance you only have. Okay. Okay. See, in this comes out of what we call estimation in statistics theory. Okay. So basically, what you have is there are natural processes which. Okay. So there are natural processes for which are your interest of study, right? You want to model those natural processes or any kind of processes, and you assume some kind of distribution there, and you want to find the mean, or you want to find the variance or some kind of population parameter. That is where you do some kind of estimation, right? Suppose you want to find mean. Now you can do you can do two kinds of estimation. One is point estimation. The second one is interval estimation. Okay, so what happens in point estimation is you perform some experiment, and out of that experiment, based on the result, you will estimate some value, some single point for that population parameter. For example, if you take mean as mu, this is the population parameter which you don't know and you want to estimate it. You perform a experiment and you say, suppose x bar sample mean. This is a well known estimate for population mean. Okay, otherwise you can also say, I will estimate mu mean using a single observation. I will just do one experiment, and whatever value I get, I will say that is the average. Valid, you can do that, but that does not make that much sense, right? Why it does not make that much sense? For every estimation, we have certain properties which we try to calculate, and one of them is called bias. Okay, this bias is defined for a random variable. Okay, so what it means is, how far away from the population mean is the expected value of your random variable, right? Suppose you take x bar minus mean. Okay, expected value of x bar is mu and population parameter is mu, so this is 0, which means x bar is an unbiased estimator, right? Not just bias, apart from bias there are other properties that we also look at. They are called consistency, consistent estimator, and there are more. You don't need to get into all this theory. I'm just telling this all that because of the question you asked. For that matter, even if you calculate bias of x, you will get expected value of x minus mu, that is mu minus mu, that is 0, right? But x bar has other properties, that its variance is sigma square by n. Variance of x is sigma square, right? So that means the variance of x is more, variance of x bar is less. When the variance is less, that means your distribution would be small, so your confidence will be more. Okay, so I mean, again, you will study all this in statistics. Now, what happens is, when you are calculating for sigma square variance, right? You have asked, when you are calculating with sigma square, for sigma square, if you are taking the entire population, what happens is you use the formula x minus mu xi minus mu whole square by n. So we'll use this notation, right? So this gives you the population variance. For that matter, if you make use of standard error of x bar, or standard error, what we do is we take this as the estimate for sigma square. Why do we do that? We do this so as to make this estimator unbiased.
Like,
Okay,
and like then we can say like a series of experiment was performed, and by like just by choosing n minus one, it is like it was seen that the variance of the sample is becoming close to the variance of the whole population. That's why we're using n minus one, like in layman's
so
term.
yes, in layman's terms, what you do is the expected value of this estimator is the same as sigma square, the population variance.
Okay, okay,
Okay,
okay.
so
Yeah.
if you calculate the expected value of this, calculate the expected value of this x whole square by n minus 1, you can do that in your free time. This comes out to be sigma square. If you put n here, If you put n here, that would be n minus 1 divided by n into sigma square, right? So a lot of people actually tell you that by subtracting x bar from xi, you have lost 1 degree of freedom. That is why you are dividing with n minus 1. That I will try to me for that kind of explanation in statistical theory, but this is the justification I have found to make the estimator of our population parameter unbiased. That is why we we divide by n minus 1 instead of n. So that is one property of estimators. Is that understood?
Yes, sir.
Okay. Actually, I was hoping to cover more of hypothesis testing also, but I think today we have paucity of time. I'll try to just introduce hypothesis testing, and maybe we'll have one more session.
Sir, one question
Okay.
on distribution before we move.
Mm-hmm.
Sir, so we are saying that the area under the curve defines the final, like the value of the p.
Probability.
So
Yes. For continuous distributions, area under
yes, sir.
curve defines the
So,
probabilities.
yeah, sir. So in case we have to find the probability from A to B, we use the area under that curve. So,
Right.
sir, like then how does the shape of the CFD matter? Like if I have two different shapes, like if suppose one CFD is having like straight line going upwards and one is going downwards, and both of them have the same area in under A and B. So then
Okay.
how does the shape of the curve matter?
Uh, which shape you are talking about? Which curve you are talking about? Is it the
The
property density function or cumulative density function?
so the so PDF.
PDF. Okay,
Yes, sir.
PDF.
So, for
So,
example, sir, if you could draw one like just a straight line going upward as the PDF,
so something like this you are talking about,
sir, and having an area one under it, and then I have
huh?
another one which has a downward slope.
Like this.
Yes, sir. So, area under like say uh, two
So
points would be
suppose,
the same.
yeah, suppose you want the area to be 1. This is a right triangle, so you want suppose this is 1, then you want this to be 2. This length.
Yes, yes, sir.
Similarly, this is 2. This is
Two
1.
and one.
Right? Okay. So how you will define this is is f of x is same as x. Sorry, it will be 0 0 for minus infinity less than x less than 0, and then you have x for 0 less than or equal to x less than 1, right, up until 1. No, it is 2x.
Two X, sir. Yes.
2x, and then from then onwards again it's 0.
Yes, sir. Sir, I get how we'll write it on
Yeah,
paper
yeah,
both the
I'm
function,
just
but
trying. Yeah,
yeah, yeah.
so you are saying how does this matter, right?
Yes,
This
sir. Like
shape does
physical significance, like
physical significance. Okay, so I just wrote it because for later on calculation purpose. Now, suppose this is for a natural phenomena. These two are for two different natural phenomena. Okay. Now, you want to calculate the probability of this phenomena occurring less than maybe 0.5, right? So, the probability, final probability here, this area would be less than this area, right? Or would be different from this area, right? You
yes,
understand?
sir.
So, and physically, what we say is the relative frequency of occurring of this any point here is quite less compared to the frequency of occurring any point here, the same point here, right? You get what I'm
Mhm.
saying?
Yes, yes, sir. So, like my like the basic question is that since we are saying that a particular point does not have has a probability zero, like
Uh-huh.
the height, like how does the height then matter? Because
Yeah.
if
See, if you are saying that the probability of this particular point, exact point 0.5 happening, then that would be zero. But
hmm
what is the relative frequency with which it happens compared to others? That
okay,
is high, right? That is high in this case. For example, here maybe 0.25 you take. Uh, so the frequency with which this 0.25 occurs is seen in your data, that is high. The frequency with which you see 0.25 in this data, sorry, this is low and this is high, right? So you take some data, collect data from this distribution and collect
hmm
data from this distribution, right? So and then maybe some 100 points or 1,000 points, you see the number of times you take point, you see 0.25, or rather the number of times you see between 0 to 2.25, that would be even better. But exactly 0.25, um, exactly 0.25 occurrence probability is zero, but relatively it can occur high. The frequency with which that point will occur is high. That is the only explanation that I can think of.
okay, okay, sir. So essentially we are saying like the probability of it is zero, but the relative frequency of that point would still be high.
Yes, or maybe you can say that if you take 0.25, you take a very small delta neighborhood about it. You calculate the probability of this occurring for any arbitrary delta, right? So even if you take a very small delta neighborhood of 0.25, the probability of this occurring, the points in this neighborhood occurring would be quite low for this and quite high for this.
Okay, okay, sir. Yes, yes. This makes sense, sir.
This
Got
makes
it.
more sense, right?
Yes, yes, sir.
Yeah. So
Thank you, sir. Got it.
yeah, okay. Okay, so I think we are over time. If anybody has doubts related to distributions, maybe they can ask today. We'll have one more session, probably maybe tomorrow, based on our timings, about hypothesis testing. We'll discuss that then. Yeah. Anyone has doubts?
Sir, what is the difference between probability mass function and density function normally?
Okay. So you have two kinds of random variables: discrete and continuous. Okay. So uh, what we call as discrete are like the random variables which can assume values that are finite or countably infinite, right? So suppose you toss a coin. What are the possibilities? What is the probability of a head occurring or a tail occurring? So this is a random variable which can assume only two values, right? No, suppose you keep on tossing a coin until the first head occurs. Now, what is the random variable? The number of tosses required to get a head. That is a random variable which can take values 0, 1, 2, so on, infinity. You can, in theory, get a head at maybe 1,000 or 10,000 times after tossing. So, in theory, you can have an arbitrary number of tosses required. So, but but that is countable. Even if it takes 10,000 points, 10,000 tosses, or 100,000 tosses, you can count till then. So as long as you can count, it is countable and it is discrete. Okay. Even another question, another example is, suppose you are calculating heights of all people in your class. The height is a continuous random variable, but if you stipulate that you are rounding off the height to maybe one decimal place or two decimal places, now the values your random variable can assume are finite, right? They're countable. So that would be a discrete now. Now, so what happens is, when it is a discrete random variable, you have probability at each discrete point. you can calculate the probability for each discrete point. But for a continuous random variable, you cannot, or rather, if you try to calculate the probability of one discrete point occurring, it will always be 0. So probability mass function, PMF, this gives us the probability masses, specifically probability masses. So for a Bernoulli distribution, which is tossing a coin a single time, it would be probability of, suppose your random variable is x and you are saying head as 1, that is half, and probability of x is equal to 0, suppose you are saying tail as 0, that is half, right? Now this is the probability mass function for your random variable. Is x is half if x is equal to 0 or 1, 0 otherwise, right? So this is the probability mass function, because you have distinct masses at each point. At 0 you have a mass of half, and at 1 you have a mass of half. And if you do summation sigma of all the masses, that should be 1, right? In continuous distributions, this kind of summation is not possible. Okay, and this kind of probability masses are not possible. You can at most say about the relative frequency of a small interval, or relative frequency of a single point, and the probability of a small interval, right? There you have to deal with integration, and you have to say integral of the entire thing, entire density function, that is 1. Okay, so there what you have is just the density uh, of the random variable, and here you have masses. These are actual probability values, but the height here does not represent probability. Okay, now sometimes you can have mixed distributions where the random variable can have some mass at a particular point and remaining is continuous. Those are called mixed distributions. Suppose you take this, so the height is 1 here, the area is 1, area is 1 by 2, and maybe it takes value 2 with probability half. This is called mixed distribution. For this distribution, this is the density and this is the PMF, probability mass, right? You got an idea of the differences?
Yeah.
Okay. Okay. So we'll end this here, and we'll continue with hypothesis testing next class.
Thank you, everyone.
Thank you, everyone.